Welcome everyone to this webinar on thermal analysis of an electronics enclosure, forced convection simulation with Simscale. Thank you very much for joining us today. My name is Valerio Marra and I'm the VP of Marketing at Simscale, and I will be your moderator today. Today's presenter is Alexander Fischer, Simscale's co-founder and product manager. Alex has a background in computational mechanics and control technology, and he worked in different roles at Simscale, from product to engineering, with the goal of building a cloud-native web-based simulation platform. Alex currently leads Simscale's effort for thermal management and electronics solutions. And let's take a look at the agenda for today. Alex is presenting, and he will go to the next slide for us. So after this short introduction, we will dive into Simscale engineering simulation capabilities for the application that we're covering today, which is electronics enclosure design. And Alex will take over soon to show us the platform live. It will build for us a simulation, a comment on the results, and then after the live demo, we will run a Q&A session and discuss how you can get to try the software yourself. Please do not hesitate to ask any questions you may have. You can do it at any time, and please do it through the chat box in the webinar panel. And now let's take a look at the reason why Simscale exists, just to give you a little bit of background in the next slide. So if you've been in simulation, you know that most applications run on a desktop, which means you have to provide also the hardware. You have to take charge of all the costs that are associated with it. And then there's in addition to learn the software, right? You have to also have to keep your hardware in tip-top shape. While if you simulate in Simscale, what happens is the hardware is not the issue. You just have to focus on simulating what is the problem that you have to solve. And then since we can rely on the latest web technologies, you also get an experience that is highly streamlined. You will see it in the live demo. So to summarize in 2 words, right? We want to provide engineers with the best of technologies, from the computational power that you have to the simplicity by which you arrive to simulate your applications. And now if we go to the next slide, we already start diving into today's problem, right? An application. So I just wanted to share with you the applications that Simscale customers are simulating. This is just a subset. Of course, we have natural force convection. We can handle liquids and gases. We can model components that you use to move air into the enclosures or in open spaces to cool your electronics. We can deal with materials that are not anisotropic. And then, of course, for the sake of simplifying your models, we can deal with thin layers and analyze power networks. So this is just to give you a sense of what we can simulate. And then we put together a couple of slides for you where you can see applications or a few names of customers that work with us. We did run a webinar a while ago with Rimac, where they discussed automotive battery cooling. But as you can see, we go from electronic motors to transistor plates and more. And then we also have in the next slide, we're listing other applications. Again, this is to inspire you, right? Because the main question engineers ask is, well, I like the software. Can it solve my problem? So this is why we're sharing with you these applications, hoping that you either see yours or you get inspired to actually model yours. All right, so this was a very brief intro, and thanks for listening so far. And without any further ado, let's have Alex taking over. Alex, the floor is yours.
Thank you, Valerio, and also very warm welcome from my side. I will show you now in a case study how Simscale is essentially working, how you can do a forced convection analysis on Simscale. We will have also further sessions in regards to thermal management and electronics design in the upcoming weeks. So also take a look at those later on. But for today, we will really look into how we set up a forced convection case on Simscale and what it helps you essentially to simulate this and use it in your design process. This is already a screenshot of our application. So it's a high density power electronics assembly. You can already see that it's in some way highly simplified. So we really want to give you an introduction on how you define these concepts and what is required, what is also sufficient to run these kind of simulations, and that's why we walk you really step by step through the full process. We will cover the physics of conjugate heat transfer. That means essentially that we will really look into all mechanisms of heat transfer in general in such a simulation. So that is convection, be it natural or forced, that is conduction in the solids, and that is thermal radiation. In our case setup today, where we look at forced convection, we will really focus on the solid conduction and the forced convection. We will have additional series on the natural convection aspect and thermal radiation specifically, while thermal radiation plays also heavily a role, usually in natural convection, not as much in forced convection. So for this series, we kept it out of the session today, and we will really focus on it in the upcoming sessions. In regards to boundary conditions and source terms, we have two inlet fans for this power electronics enclosure. We use here a constant flow rate for simplification. It's obviously also possible to just upload a fan performance curve and really get the flow rate as a result of your simulation as well. We use a pressure outlet, simply an opening of the casing on the other side. Add some natural convection wall boundary conditions. When I show this on the platform, I will also explain you a bit essentially how you can combine here a forced convection and a natural convection simulation if you're not confident on what the natural convection coefficients on the outside might be, or how big the contribution of a natural convection on the outside actually is. And we will use obviously various thermal loads on the chips, capacitors, etc. So we have many different thermal loads in this assembly. At last, once I showed you the whole setup of one simulation, we will really also look into why this shouldn't be one simulation, why simulation is so helpful in iterative design studies and also in parametric studies. So we will look into how can we then run or test multiple design iterations that we performed, but also how can we use parametric studies to gain really early in the process information on what might be really the optimal scenario kind of upfront of designing. Good. And with that, I will now switch over to the Simscale platform. What you can see right now is that I'm just switching now tabs. So I am right now in Google Chrome browser. You can see on the top right my face essentially. So I just logged onto my Simscale account as I would log into LinkedIn or any other platform that you might know. And then I can just enter my workbench, in this case, this project, so this electronics cooling CHT webinar project. And you see on the top that I have here this unique project URL. So I'm really just in Chrome browser. That is also what you require for Simscale, a standard internet connection and a standard web browser. That is all you need. I'll quickly now move this to full screen. So this feels then maybe even more like a desktop application, but we are still a really cloud-based web application. And you can see on the very top here a couple of symbols, and I'll give you first a quick introduction on what is really different about Simscale, and then we see how the simulation setup is done that is more comparable to what you might know from other tools, but I will also give you some indications on where we really focus on making the user experience for you easy to understand, and where we try to get you started with a simulation much faster than you might be used to it. Okay, on the very top, you can see here a little indication that this is a private project. That means my project, even though this is now accessible via this web interface, is private and only accessible by me. That is also how our customers operate. But we also have content that Simscale created that is public, and we have hobbyists and enthusiasts that simulate in our community that help essentially educate, that want to show off the great products they are building, and this can help you as well to get started using the platform. But that is why you can see here that my project is private only. Even though it's private only, I can still share my project, and that's one of the big differentiators that Simscale allows you to do for two reasons. One is I can share this with a colleague and set the permissions that he should have on my project. So for example, if I'm working with my colleague on a certain design study and he should take on and do some additional simulations on top, I can just give him can edit permissions and he can work collaboratively with me on this project. If I'm having a colleague that should just do a new design iteration based on the results, or if I want to give my customer maybe even view access so that he can gain some insights on where we stand with the project, I can also pick here can view, and then he cannot modify my project, but he can still have a look at it. The second way how this is helpful is that you can use the same mechanism to share your project with our support. Why you would do this is that if you face here inside of Simscale any question, a challenge, potentially how you should model something, so anything that might come up now in the presentation that I'm doing, you would usually now click down here on this little bubble, and then you can can ask a question to our support team, more or less all around all different time zones. We will answer it within a few minutes. So there's no need from your side that you file any support ticket, wait for this to be picked up in progress and resolved, but you can directly interact with us and get help from our support team. And if you do so, then we recommend that you share your project with us, because then we can jump onto your project. You will also see our avatars appearing here, and we can directly help you with your simulation. So that makes it essentially all of these situations you might from other onboardings with software tools where you got stuck in a certain workflow, you can just skip by asking a question and getting direct help. Good. That was a first introduction to what Simscale, what's special about Simscale. I would now want to really show you in detail how a first convection case can be set up. That's why what you can see here is already results of our enclosure design, but we will now not dive into the results. We will first now look into how can we prepare our CAD model to be simulatable on Simscale. We will secondly look then into how can we set up a simulation on Simscale, really step by step. As a third step, then we will get back to this view and we will look a bit into the results quantitatively and qualitatively. And then we will, as a last step, also look a bit at how can we expand our simulation usage and really support our design workflow by running kind of massive amounts of simulations and doing different kind of studies. Okay, without further ado, then I will go back now to the geometry section. You see here on the left-hand side, we have here the geometries I can bring in and the simulations. If I click here plus, we can just import a model from our computer or import it, for example, from partner frameworks, like in this example Onshape. We support all common CAD formats, generic ones as well as native ones. So if you're from the electronics world, you likely will bring in a SolidWorks Inventor, Creo, or if you're from the automotive area, also CATIA file, and just import it into our platform. When you do so, you can see here our model that we want to look at today. I'm hiding the casing and flow region. And you see here we have a lot of different components where we will put the heat load on. We have this big chip with a heat sink on top. This is also one of the design iterations that we want to do. But this model was already prepared now for simulation. So we will rather now take a look at the same model without the flow region already being defined. And I will now switch into our CAD mode to show you how you can prepare your model for being simulated. You might be very well used to the user interface that you can see here. It's very similar to other CAD environments, but we are not a classical CAD tool. We just want to support you bridging the gap between a CAD that was successfully done in the CAD environment and is maybe manufacturable, but it might not be very well suited for simulation in all cases. In those cases, we want to bridge this gap and want to be the complete solution that brings you from CAD to design decision, and that's why we expose some special operations on top. So if I'm hiding here as well the casing, you see that this model was already simplified a lot, but I can give you some impression by just selecting, for example, this little component down here and replacing it I selected here geoprimitive box. So now we will just enclose this shape by the closest box. Essentially in electronics assemblies, this is often very helpful because many of the parts that you might have in here, you can see now this replacement happening. You might have many small components that you want to have in the assembly because they might affect the flow pattern maybe, but they are not super relevant for the heat path or the thermal behavior of the system, and might be very geometrically demanding and detailed, and then you can just get rid of those. Or you can, for example, just delete certain faces within components, fillets, chamfers, etc., and even make these components even simpler than before. Good. If you're happy essentially with your model, or you didn't even want to simplify it and rather use the more or less unlimited computing power that you can later access and just mesh as you have the model, we will still require now a flow region. So we don't have a representation of the air inside of this package, as it's usually the case when the CAD or kind of the model comes out of CAD design. So what I will quickly do here is create an internal flow volume. So it asks me to pick a seed face. This tells the algorithm essentially where's the inside, so in which direction should I extract this flow region. I'll then select the bounding faces, so here on the fan inlet and on the outlet side, and then I just click apply and wait for this to be done. So this will create now my flow region that I can use later on to assign air and also use it for the boundary conditions later on. Good. Yeah, I will now just exit CAD mode again as I prepared this model already for our simulation. And I will now create a new simulation. So we get from the first part, CAD preparation and import, now to our second step, create a new simulation and how the setup can be done. So I'll just click my CAD model, create simulation. I can pick from a huge amount of analysis types. Simscale is really a platform, so we try to do all the UX concepts in the same way. It doesn't really matter if it's flow or structural, but we still have here some distinction in analysis types that allow you also to, from the description and these images, find easily a way of which of the analysis types likely supports you most in doing what you're looking for. In our case, we want to see really the heat transfer in this assembly, and we're going for a conjugate heat transfer analysis. So I'll create this simulation, and what is happening now is that I get inside of my simulation section a new simulation with a navigation tree that shows me a couple of different setup steps. And within these setup steps, you can already now see a few icons in here that are colored in different colors, in green, red, and blue. That is because we want to expose you many of the settings that you might want to look at, or at least we want to give access to expert users to many of these settings, but they're not actually required. So we have the chance essentially to use the expertise in-house of Simscale, but also to use the data that we collect from our community users and hobbyists to make the best settings possible for you and make this really robust. So many of the settings, like for example, numerics that are very expert settings, or even the meshing, we do automatically. So we take all of your setup, etc., into account to create the best mesh possible for your setup. So you don't need to touch this if you're a newcomer to simulation or you're not really interested in those settings. You really need to care about the red sections, because that's where your input is required. That's where we cannot really make estimations, and the blue sections are optional. So they don't need to be there. In our case, we want to have solid conduction as well, so we will create both fluids and solids. So we'll start essentially adding here just air. Materials are the first setup step that we want to do. So I'll select now the flow region that I previously created. It highlights it now here in the viewer, and I just hit apply to assign it. I'll also add now one solid material for you from our library. I'll just take copper here for the heat sink, assign it, and again hit apply. I'll keep the other parts right now not assigned. I'll show you this in a completed setup later to just show you the concepts one by one now in this new simulation. Good. We want to have boundary conditions as well. So this is a forced convection case. So we want to push air into this. We have two fans here on this side. In this case, I'll just pick a flow rate with a volumetric flow, use here a value of 0.00467 cubic meters per second, and assign this to these phases here to get in total 0.014 as a flow rate that I want to have in my assembly. On the other side, I will add a pressure outlet that just represents essentially open environment on this side. I'll keep the walls now for what it is. I show you this as well in the completed setup later, and I'll move on to the power sources. I'll create one power source already, move in here. Maybe we just take here now this large chip in here and assign 10 watt on this, just as an example. Hit apply, and now you can see that already this fills up, becoming all green. So you know now my simulation is simulatable. I can now start the simulation, but it might be that I still did not add everything. So I'm clicking start, and Simscale now gives me some feedback on what is missing. So it tells me there was no gravity defined. If I would be running now a natural convection analysis, this would be crucial because the flow just comes from the Boussinesq effect, so kind of from density changes based on the gravity. In our case, for a forced convection case, I might very well neglect this, but what I shouldn't neglect is here that there are some missing material assignments, and that just comes from me only assigning the copper to the heatsink and leaving all other parts out. So Simscale will also help me essentially before I start a simulation if I did everything that is required to run this. Good. Then let's jump into a completed setup. I don't think it makes sense that I show you all of the different material properties, but we can now really walk quickly through the completed setup. So you can see now we have here aluminum only on the casing. If I show all components again, then we have here the aluminum. We have here different materials. We have, for example, here for the boards, a low conductivity material that was chosen, and again the copper for the heatsink. Additionally, the boundary conditions are the same as I did in the new setup, but now in this case I also added here the heat transfer coefficient setup. So we put here natural convection boundary condition as a wall on all outer surfaces that are not inlets or not outlets, and put here a heat transfer coefficient of 10 watt per Kelvin and square meter. So usually for natural convection, we have these values ranging from something like 5 to 10 for air convection. If I'm not comfortable doing this, I could also now add in CAD mode an external flow volume around the whole assembly and simulate the natural convection as well, so that I don't need to make an assumption on this. And you can see how this works in our next session on natural convection. For the advanced concepts, so looking at the power sources, I created many different ones just simply because these thermal loads are very different in value. So for the capacitors, maybe I'll hide those parts again to make it easier to see. The transformer, the different chips, we have different power values. So I created all of these and simply assigned those to the setup. And now we have essentially all the correct physics covered, and we can look a bit more into how do we run this simulation. So to make it really easy to understand, and also see during the simulation where we stand in regards to critical temperatures, I created one result control item on the top face of this chip. So this will allow me to track in a 2D plot the temperature distribution, or kind of the temperature value on this chip. And I also want to quickly jump to the mesh that was created up front here. So you can see here, this is now our mesh. We can hide also here different parts and look how it looks on the inside. I created a very coarse mesh so that we can have a quick turnaround in the simulation. We are around 1 million cells in this assembly. And also here you see that there's some automated settings that allow you to just click start and run the simulation. We're taking the physics that you defined for materials, boundary conditions, and source terms into account to make this the refinements on the model the best way we can. So for example, we apply some boundary layers on the fluid regions, etc. But you could also change to manual and do the refinements very detailed yourself. Good, that would be then the completed setup. So this is where kind of the second part of what I wanted to show you in that sense already ends. I'll quickly click start though for the simulation. Here I completed the setup, so I don't get any warning or error that tells me that I need to do something to start the simulation. But I get also here some information that might be kind of helpful for you. So there's a resource estimation based on kind of the data model that we have in the back, so that we can tell you that based on the simulation setup and based on the control, so kind of the number of cores, etc., that you picked, how long the simulation will roughly take you and how many computing resources you would require to run such a simulation, so that you know upfront how long this will roughly take. With Simscale, you can always simulate, and obviously we don't require any attention on your machine or your computer, so it just runs in the background, or even on the weekend or on your way home. You'll also receive an email when your simulation is done, so no need to stick around, but it's anyways helpful and pretty nice to have a rough estimation when you will be done with the simulation. Good, then let's look at the simulation results. I created this result control item so we can take here a look at how over the iterations during this simulation the temperature on the chip evolves. I'm putting here the temperature out every 10 iterations, and after roughly 300 iterations, this is fully converged and doesn't change anymore. We are here in a steady state setup, so we want to really disregard transient effects, and we should get really a nice converged solution around a fixed temperature then on all components. We reached this here, and we can take a look at the 3D results to gain more insights on how we can improve our design. Good, so this is our post-processing environment. What you can see here now is the temperature in degrees Celsius. We chose here a temperature color scale that might remind you of thermal imaging. So you can see here the different temperatures on the components. And next to this, we have here a cut plot through the model where you can see the flow field. You see it colored from blue to red, red being high velocities, blue being zero velocity in this case. And we also have some vectors or arrows here in the model that show us essentially in which direction the flow is directed at all points in this cut plot. So the temperature results obviously are more suited to give us a quantitative insight. So what is the max temperature, for example, in our model? The velocity field, for example, is more qualitative. But often if we find essentially critical temperatures to be too high, we will find the reasoning of this in some qualitative insights. I'll show you this also in a second. So if I would now quickly change the coloring of our parts here to solid color and make it transparent so that we can see this nicely, and hide the cutting plane over here, then I can switch on here a so-called ISO volume filter. So what I did here is essentially I want to just see regions now in the model where my temperature is higher than 58 degrees Celsius and up to the maximum temperature. And I can now see, okay, this is more on the right-hand side of this assembly where I have these high temperatures. I could also move this to different temperature values that might be helpful for me. But we know, okay, the highest temperature we have over here, and maybe we now take a look at why this is the case and switch back to showing a temperature here, maybe also again in shaded view. So we see, yeah, over here we have high temperatures specifically now on this part, and we want to see why this is the case. And for that reason, I'll switch on this cut plot again. And what you can see now here is that we have obviously good velocity next to the fan inlets and to the outlets, and also here around the heatsink. But down here we have we have in blue very low velocities. That's a bit different on the left-hand side, as the boards are all oriented in this direction. So on this side, we have still quite some good flow around, for example, these parts over here. But here it's really, really dark blue. I can also maybe increase the size of these arrows a bit. Yeah, so there we can see here, we have here recirculation zone. Specifically, this part does not get essentially any significant cooling from the airflow, and that is likely the reason why we have such a high temperature on this part, also on the board next to it. So this would be really a point where we could make some adjustment, place components differently, the fans or the boards, or do something so that we get a better airflow around this. Additionally, maybe I can show you on a second cutting plot. We can also take some insights on, if you move this to the inlet, we can look here, for example, into what's our flow rate. So that might be specifically interesting if we would be looking here at a fan performance curve. So we could enable the statistics on this cutting plane. And this will show us essentially the flow rate, volumetric flow rate on all of these faces. Here I fixed it, so we will have these 4.66 on all of these faces, but for a fan performance curve, I could now look at this, or I could check on the pressure field to see what's the pressure drop in my assembly, what's the operating point on the fan curve that I reached via this, and gain some insights if I should replace the fan, if I should add additional fans, or at least change the positioning of these components. Good. That was the third part I wanted to show you. This is how do we gain some insights from the results that we simulated beforehand. And let's now also look at how can we do iterative design studies and how can we do parametric studies. So if we, for example, want to now run one simulation also on this pin-fin model that I can quickly show you again, we could now just take one of the simulations that I'm having here, duplicate this simulation, switch the geometry to this pin-fin with flow region, selected. And what you now can see is essentially that all of the settings that I had for the solids and fluids for this specific model, as it's just one design iteration that I created on this model, stay intact. So I can still run this model as it is. You can see that the contact section gets now updated because obviously the contacts now between the flow region and the heatsink are different. I'm now having likely much more contacts because I have more surfaces from this pin-fin heatsink, but all of the rest of it stays intact. I don't have a mesh anymore because I did not create this yet, but if I run the simulation afterwards, this will be automatically calculated as a first step. And now also the contacts are done, and I can see now that I have a few more in here between the pin-fin heatsink and the model. So this allows me essentially, if I would have now gotten feedback from my first result that I need to change something, that this chip gets too hot, that I should rather use a different heatsink, I can now just add a new design iteration, switch the models quickly, run the same setup and get results very fast. If I don't have time for doing this, or I want to test multiple of these iterations at the same time, obviously I can also just kick all of them off at the same time. That's the big benefit of the cloud environment, that we can really run all of these simulations at the same time, and that the turnaround time for you gets down to the turnaround time for one simulation for all of them. So then you can also easily compare those and make smart design decisions based on this. One additional point that I wanted to show you is that I can also run a flow rate study. So let's say I would not right now have a fan already picked. I would rather want to see which flow rate do I need to have, right? What is the pressure drop, and which component should I pick? So which one should I get from a supplier? So in this case, I again chose a volumetric flow rate, but I now provided a table input. So just that this is a step function, I provided 4 different values. the first one being the same flow rate that we looked at in the first study. And now I kind of ran 3 different ones, so kind of cutting this by 4 and then using these different flow rates to see would it be already sufficient potentially to only apply those, and ran this simulation as well. And if we now look at the results of this simulation, we will see very comparable or very similar results. From this, obviously also for the first step, they will match the same results that we had beforehand, because that's just the first flow rate matches what we did beforehand. But now I can switch here to the next iteration where I ran after the a bit lower flow rate, and then the one after and even more. And you can see down here, for example, how now the temperature, the hottest temperature of these components, these components goes up, and for the lowest flow rate now reaches the highest temperature. So we had 73 degrees as the hottest temperature beforehand, and now this is 88 degrees. So that also allows us essentially to look at different flow rates. We can run as many as we want, so you might just pick what is a reasonable interval between those values to figure out what is really the best way to treat this, and work with those values to make a good design decision and optimize your assembly or your design. Good, those were the 4 steps I wanted to show you. So essentially CAD preparation, simulation setup, result assessment, and how I can really make use of massive simulation to gain insights and be faster in the design process. I'll now switch back to our slides. Good, I'll pass back to Valerio at this point, I think with a Q&A.
Thank you, Alex, for the great presentation and live demo. A nice time to take some questions from the audience. We got quite a few. We'll do our best to answer to all of your questions in the remaining time, and we will get back to you after the webinar in case some questions will go unanswered. So let's see. The first question is, Alex, this application, what was that exactly? Was the cooling of a CPU or another kind of equipment?
Yeah, so the big chip was meant to be a CPU here, and then we have these sideboards. But the reason for this model is really kind of we use it almost for educational purposes. So that's why also all of these components are very simplified. I can also recommend, if you're now running your own assembly, your own electronics enclosure, we also have webinar content. For example, our webinar on skip CAD simplification, where we show also how you can do exactly these same kind of simulations on very complex models and how we treat these then in the setup. So this is more kind of an abstract way of showing how these physics work, and it makes it kind of helpful to show what different physics and what different effects take place without having too many details on the model. But it's a CPU cooling essentially.
Right, thank you. And a question about capabilities. Can we model thermal radiation?
Yes, we can. So in this case, I consciously decided to not include it. You also saw that I didn't include gravity, as we didn't put a natural convection box around the rest of the assembly. We will really dive into details on thermal radiation for the natural convection and specifically the thermal radiation webinar in the upcoming weeks. But all mechanisms of heat transfer, so thermal radiation, convection, if forced, or natural convection, and conduction are possible with the same solver, so all coupled.
Great, thank you. And one last question is, how can we, try the platform? Is it easy to use? Do we have any, tutorials or material available for engineers and designers to learn how to use the software?
Sure. Yeah, we have a lot of content out there. So you can dive into our documentation where we collect all of this content. So there's a knowledge base out there for specific problems. There are tutorials. There are also validation projects for simulation. It's always important that you understand what the quality of your results are, and that's why we expose also these validations at this same point. But you can, for specific purposes, for specific features, use all of our tutorials that we have out there. But you can also search our community for potential power users that might do really a very similar application that you do. And if you face a specific problem, it's always the best essentially to directly reach out to our support team, as they can help you best essentially on what you require.
Great. So thank you, Alex, for answering the questions, and to the audience for engaging with us. And then a couple of more slides, and then the webinar is over. So we just wanted to share with you, if we go to the next slide, why we do what we do every day, right? We're engineers ourselves, and we feel the pain of using outdated tools and experience. And basically here, we summarize what we do. And created this product so you can simulate at any scale, since we're in the cloud, which means you don't have to limit the accuracy of your model. And then from pricing to ease of use, it's accessible. So we want also to open up simulation to different industries and companies and size, the company, irrelevant of the size of a company. And then in the next slide, we summarize also what are points that are unique to us. Just a few of them. Again, the accessibility, also this workflows that are very lean, minimalistic, very simple to start using the software, and again the practically limitless power of the cloud on demand, so you can get accurate simulations and results fast. And then something that it's also very important, that can only happen if you use a cloud native product, is we can do in-product support. So if you get stuck, you can call us and we can get back to you real time, and we can help you with the model. And now a few remarks before we conclude. Let's see how we can get you on the Simscale platform. Well, you can just go visit our website or contact us via email, and we'll get in touch with you within one business day. All right, and thank you so much for joining us today, and we hope to see you on the Simscale platform very soon. Thank you again, Alex, and thank you for the audience for staying with us. Have a great rest of your day.
Thank you as well. Goodbye.